In this video, we will learn about functions. We will look at lines, quadratics, exponentials, circles, sinusoids, and many other examples. We will learn how to sketch them and how to understand their domains and ranges. We will also learn how to classify a graph as one-to-one, many-to-one, or not a function at all. By the end of this video, you will have mastered the fundamental principles of mathematical functions. Let's start with a simple function. f of x is x plus 2. This means that whatever value x has, f of x is always 2 more than that. So for each value in the x column, we add 2 to find the corresponding value of f of x. Once the table is complete, we can plot each point from the table onto the graph on the left. Then, by joining these points, we can get a sketch of the function. We also need to specify the domain. In this case, the domain is all real numbers, which is shown by the expression being animated now. At a particular value of x, say x of 3, the blue curve gives only one value of f of x, which is 5 over here. As we move across different values of x, the dashed lines and cross show that each input gives exactly one output. Since this graph also doesn't repeat any f of x value for different x values, we call it a one-to-one function. Now let's move on to another function, x squared. From now on, instead of saying f of x, we will just say f for brevity. Just like before, we can calculate a table of values and use it to sketch the curve. This time, we choose 2 different values of x, draw dashed lines to the curve, and notice something interesting. Both points give the same value of f. For example, an x of 2.5 and x of negative 2.5 both give an f value of about 6.2. In fact, for almost every positive value of f on the graph, there are 2 different x values that produce it. The only exception is f of 0. This is why we call it a many-to-one function. The table shows the same idea. The positive and negative versions of the same x number give the same f of x value, because squaring removes the sign. Now let's explore the relation f squared equals x. We start by preparing a new table of values. Then we sketch this curve on the graph. For a given value of x, such as 6.3, we can get 2 different values of f. This happens for every positive value of x, except when x is 0. In this case, x cannot be negative. The table shows the same behavior. A single x value can produce both the positive and negative versions of an f value, which is not allowed for a function, and so this is not a function at all. Now let's look at another linear equation, but this time, instead of allowing all real numbers, we say it exists only between negative 4 and 5. Let's sketch the line. keeping in mind that it stops at the lower and upper ends of the domain. The coordinates of these two endpoint values are shown in red. We call the set of allowed x values the domain of the function. The set of output values goes from -5 and all the way to 13, and this is called the range. Now let's explore a quadratic function. This time the domain is from -1 to 9. The function reaches its minimum point when x is 3. This happens because the squared term becomes 0 there. That gives a lower endpoint of 8. For this new function, we need to change the axes and remove the old graph. Let's mark the minimum point on the graph. Next, we evaluate the function at the minimum value of x, which gives 24. Then we evaluate it at the maximum value of x, which gives 44. Let's mark these two endpoint values on the graph. Now we can sketch the quadratic curve using the three crosses. The range of the function is from 8, which is the minimum point, all the way to 44, which occurs at the rightmost point. The next function we will explore is a sinusoidal one. This one exists for all real numbers. Let's sketch the sine curve. When we draw a horizontal line, it intersects the curve at multiple points. This means the graph is not a one-to-one function. The same thing happens for many other values of f, but intersections only occur when f is between -1 and 1. Now let's turn the line vertically. For any value of x, the vertical line cuts the curve at only one point. That's good, because it means the equation is indeed a function. Based on these observations, we can conclude that it's a many-to-one function. Its range is from -1 to 1. Now, let's restrict the domain from -2 pi to 2 pi. Within this domain, there are two full periods, the blue portion and the red portion. We can reduce the domain of the function, but at this stage, the range has not changed. Further restrictions, however, can affect the range. The sine curve was many-to-one before, but is it still many-to-one now? No, it's not. For each value of f, there is now only one corresponding value of x. That means it has become a one-to-one function. Next, let's explore an exponential function. First, let's modify the axes. Then we sketch the curve. Now we draw a horizontal line, and it intersects the curve at one point. For any value of f, there appears to be at most one intersection. At f of 0 and below, there are no intersections at all. So we can conclude that this is not a many-to-one function. Now let's turn the line vertically. For any value of x, the vertical line intersects the curve at only one point. That tells us that it's a function. And since we already saw that it cannot be many-to-one, we conclude that it is one-to-one. For a power-like formula, no matter how much we decrease the value of x, the function value gets closer and closer to 0, but never actually reaches 0. As x increases, the function value keeps increasing monotonically. In other words, it only increases and never decreases, which also confirms that it is one-to-one. The range is all real numbers greater than 0. Now let's explore what happens when the domain is limited from -3 to 3. If we change either the lower bound or the upper bound of the domain, the range changes as well. Now let's explore the equation of a circle. The right-hand side is the square of 2. This tells us that x can have a maximum absolute value of 2. Let's change the axes, and then we draw the circle with a radius of 2. When we draw a vertical line, it intersects the circle at 2 points. Once that happens, we don't even need to test with horizontal lines. We already know that it's not a function at all. Now let's say we have a quadratic function from x of -3 to x of 2. We also have a linear function from x of 2 to 4. This is called a piecewise function because it's made from 2 separate pieces, a blue piece and a red piece. First, let's focus on the blue part. The left endpoint is at x of -3, where the function value is 0. So let's mark that point on the graph. Next, we find the maximum point, which happens at x of 0. At that point, the maximum value is 9. Let's mark that point as well. Finally, we find the right endpoint at x of 2. The function value there is 5, so let's mark that too. Now we can join these markers with a smooth quadratic curve. For the red linear piece, the y-intercept is at 1, so let's draw the line. But we need to remember that this piece also has a restricted domain. Let's remove the crosses to make the graph cleaner. As before, we introduce a vertical line and move it around. No matter where the line is placed, there's only one intersection. The most important location is where the blue and the red pieces meet. At that point, there's still only one intersection, because both pieces have the same value there. And so it's a one-to-one function. Our final example is another piecewise relation, where the blue part is a quadratic and the red part is linear. As before, we begin with the blue piece. We find the leftmost point at x of 0 and mark it on the graph. The minimum point also occurs at x of 0 in this case, so it's the same point as the leftmost point. The rightmost point occurs at x of 2. The function value there is 5, so let's mark that point. Now let's sketch the quadratic by joining the markers. Next, we sketch the red line piece, while keeping its domain restrictions in mind. Let's clean up the markers, then we introduce our familiar vertical line. As we move it around, it may look like a well-behaved function, but hold on. Let's take a closer look at x of 2. Here we can see that there are two different intersections, because the red and blue pieces have different values. This means it's not a function at all. Even though it's not a function, it still has a range from 1 to 5. Please consider liking, commenting, and subscribing to support the amount of work and the long hours that went into making this video. But there's still a lot more to learn about functions. The next video is on composite functions, and it should be on the screen right now.